Hello, everyone. Thanks for joining me today. My name is Hossam Barakat, and I work as a lead consultant with Telstra Purple. Today, we're going to talk about microservices and how would we empower microservices using Istio Service Mesh. My agenda for today is to talk about what is service mesh in general, and then we'll spend the rest of the talk focusing on Istio. So we will dig into what is the Istio main building blocks and its architecture. After that, we will spend the rest of the talk showing you how would we leverage the Istio capabilities from traffic routing, reliability, and observability and apply them on a real-world microservices application. So why we should care about Istio Service Mesh or Service Mesh in general? A lot of development teams have started their journey in breaking their monolith applications into a set of microservices, or even building their new applications using microservice architecture. Microservice architecture in general has a lot of benefits from modularity, autonomy, and flexibility. And in a microservice-based architecture, each microservice should be deployed independently. And thanks to the container technology, we can easily achieve that. So I'll build my microservice, containerize it, and then push it to production. But the container technology itself brings a bunch of challenges. How could we have fault tolerance? So if one of the containers died, another one will be automatically spinned up. Or how could we scale the number of container instances that I have to match the demand coming to my application? How could we have service discovery? And a bunch of other things required to run microservice-based environment. And thanks to container orchestration platforms such as Kubernetes, a lot of those challenges have already been addressed. But there are still few challenges that we need to address because those microservices will need to communicate with each other at a certain point. And when we think about this communication, we need to make sure it's reliable, secure, and we can observe all those service-to-service communication. But there is a bit of a challenge there because previously the microservices were living on the same host. So we didn't have much a challenge in terms of communication. But right now, they are going to communicate over the network. But how hard could it be to have a real-time, reliable, and secure service-to-service communication? If we take into consideration the fallacies of distributed computing, which is a bunch of false assumptions that as developers we make about distributed systems, such as network is reliable, latency is 0, bandwidth is infinite, and the rest of the assumptions. All of those assumptions are pretty much false assumptions. So when we think about those, we will find it's really challenging to achieve a reliable connectivity between the services. But as developers, we try to solve those problems by thinking about abstraction. So we try to abstract those infrastructure network-related concerns and use libraries. So in the .NET world, we could be using something like Puli that would provide us with reliable connectivity. So we could have like retrials, circuit breakers, and a bunch of other features. So our application will be something like this. We will have two services that would like to communicate with each other, and then we have a bunch of libraries providing us with those resiliency features. But then in a microservices environment, each microservice could be written in its own language. So at a certain point, someone will come and say, it makes sense to write this new microservice in Elixir or Clojure or Haskell or whatever language that makes sense because it fits this problem domain. And at that point, you'd realize, do I have to solve the same problems that I solved just in C# on whatever language that I was working with? And the answer is yes, because it's different language. So you might need to have another library. And with using another library, there is a challenge there because some of those resiliency things doesn't have a standard. So it means that we will have inconsistencies in terms of the implementation between the services. And as developers, what we would do is apply another level of abstraction. So we should extract those infrastructure concerns from within the service to be outside the service, because they are really undifferentiated heavy lifting, unless your company main business is to build those infrastructure-related concerns. So we end up with what's called the Sidecar Proxy pattern. So we have our service will be split into two components. The first one contains our business application, and the second one is a Sidecar Proxy, which is intercepting the traffic going in and out of my service and applying all of those infrastructure concerns from retries, having security in terms of the communication. We can also leverage it to apply traffic routing capabilities. So we can have advanced traffic routing. So we could have split the traffic to 80% to one version and 20% to another version. And the Sidecar Proxy is the core pattern that the service mesh platforms have been built on top of it. The service mesh platform in general is a dedicated piece of infrastructure responsible for connecting, controlling, and observing any service-to-service communication. And it's typically implemented as an array of sidecar proxies living alongside the application. So each service will have a sidecar proxy living beside that service, and that sidecar proxy will be intercepting the traffic in terms of service-to-service communication. So it enables us to apply a lot of traffic routing capabilities. And it doesn't have a centralized server that I have to communicate with all the time. But where would those sidecar proxies get their configurations or traffic routing rules from? They will get them from the control plane. And the control plane responsibility is to get the rules and configurations from the users and push them to all of the sidecar proxies living inside the mesh. There are multiple service mesh platforms available right now that we can leverage, but today we will be focusing on Istio, which is an open source service mesh platform that provides us with a uniform way to connect, control, and observe the service-to-service communication. So let's dig a little bit deeper into Istio and its main building blocks. So to understand Istio, let's assume that there are two services would like to communicate with each other. Service A would like to communicate with Service B. This could be over any protocol like HTTP 1.1, 2, gRPC, or TCP. Once we deploy those two services on top of service mesh, each service will have a sidecar proxy living alongside this service. And it will be automatically intercepting the traffic. So I don't need to modify my application code to get those benefits. So this means that the traffic right now will be going from service A to service A proxy, or automatically intercepted by service A proxy, then goes to service B proxy, and finally will go to service B. And the response will go back in the same path. And then, so this is representing the data plane. What are the control plane components of the Istio service mesh? The first component is the pilot. And pilot accepts the traffic routing rules from the users, push them to all of the sidecar proxies living in the mesh. Second component is the mixer. And mixer provides us with two key benefits. The first one is policies, and second one is telemetry. So policies means I can start applying traffic routing policies for any service-to-service communication, because whenever a call happens between two services, before the call proceeds, the sidecar proxy will go and ask the mixer, am I allowed to do this call or not? And if I'm allowed, then the call will proceed. And after the call completes, asynchronously, the sidecar proxy will be sending telemetry information to the mixer. Then the mixer will grab those telemetry information, share it with other monitoring platforms, as we will see later. Finally, the Citadel, and the responsibility of the Citadel, all of the security-related aspects in the service mesh. So if I would like to encrypt the traffic between the services, or all of the services in the mesh, the Citadel will be generating the certificates that could be used for encrypting the traffic. And this is basically the architecture of Istio. We have the data plane represented with the sidecar proxies, and then the control plane, which is pilot, mixer, and Citadel. Istio itself could be deployed on multiple platforms, but today I will show you how would we leverage Istio features on top of Kubernetes. And to do that, I would like to make sure that all of us have a shared understanding about two key concepts with Kubernetes. Before we do that, how many of you have heard of or used Kubernetes like right now? All right, so that's a good number of people. So for those who didn't use Kubernetes previously, Kubernetes is a container orchestration platform that enables us to run containers at scale. So if I have a large number of containers and I would like to execute those in a production environment, I would usually use Kubernetes. And in order to deploy a container on top of Kubernetes, the containers will always be living in what's called a pod. So a pod is the atomic unit of scheduling inside Kubernetes. Our container will always be living inside a pod. It will never ever be living outside a pod. The pod itself might have multiple containers living inside of it. And those containers will be sharing the same network namespace. And because they are sharing the same network namespace, it enables them to communicate seamlessly. And as you might have guessed, this is how the sidecar proxy pattern has been implemented on Kubernetes. You deploy your application inside a pod. The pod will contain two containers. The first one is your application, and the second one is the Sidecar Proxy provided from the service mesh. The second key object that we need to know about Kubernetes while we are working with the service mesh is the service. And the service is an abstraction that enables us to logically group set of pods and using a label selector. And label selector labels are basically a set of key values that could be assigned to any objects. So each pod will have a label, and we use the service to group those labels. The service also have a DNS record that could be used by the consumers. So my pod here, if it would like to communicate with any of those backend pods, it wouldn't need to recognize the IPs of those backend pods. It will just use a DNS record. In addition to having a DNS, the service itself do apply some load balancing capabilities. It's pretty limited though. So those are the two key concepts that we need to know about when we use Istio service mesh on top of Kubernetes. So I'd like to spend the rest of the talk showing you how would we apply the capabilities of Istio using a real-world microservices application. It's pretty simple. It's showing a bunch of products. And if you click on one of the products, it will show us the product description as well as the reviews of that particular product. The reviews has two versions. V1 is the one that we see right now, and V2 is the one with those little stars. The application consists of 3 microservices. Web, which is ASP.NET Core application, accepting the requests from the user and returning the UI. Product catalog and reviews, they are back-end services exposing the product information and the product reviews through a set of RESTful APIs. So what we will do today is we'll deploy those 3 microservices on top of Kubernetes. Then we will inject the Sidecar proxies for each service so we can start controlling the traffic going between the services. After that, we'll see how would we apply advanced traffic routing so we can split the traffic between the versions using multiple approaches. So the first one is we'll have a percentage based, so 80% of the traffic goes to V1, 20% goes to V2. Also, we will apply a role-based routing, so if the logged in user is an administrator, we'll send the traffic to V2, otherwise send it to V1. Also, we'll apply some of the reliability features. So how could we make sure that our application is reliable if one of the downstream service is too slow, or actually it's faulty, it's not available, or anything like that. Finally, we'll see how could we have a holistic view of our system. So if something went wrong, we can easily identify the source of the failure. So let's start with actually deploying the 3 services on top of Kubernetes and start injecting the Sidecar proxies to each service. So the source code of the application is available in GitHub. I will share it at the end of the talk. And all of the demos that I will do today is going to be on a Minikube cluster on my local machine. So to deploy the 3 microservices, we will deploy, for each service, we'll deploy 2 objects, the pods and the service sitting in front of the pod. And the way we do this, so for example, the Espresso shop web will be using a deployment object. The deployment object is an object that enables us to spin multiple pods of the same structure. So in here, we will be creating a pod for the, deployment for the Espresso shop web with only 1 replica. So we'll only have 1 pod. And in the spec section here, we define how that pod will look like. So the pod could have multiple containers inside of it. And in this case, we only have 1 container. The Istio service mesh proxy will be injected in as we will see later. So we define the image of that container. I am using the image pool policy if not present. This is to not depend on the internet for the demo, but if you are using in a production, you should have always. And then the name of the container will be listening on port 80, and it has 2 dependencies in terms of environment variables. The first one is the product catalog URL, and this is the key thing to notice here is the name of the DNS record that you are using. This is the name of the product catalog service that we will create in a second. And similarly for the reviews. So this is how would we create the pods of the Espresso shop web. Then we have a service to accept the traffic from the consumers. So the service itself is pretty simple. We use a label selector. And in this case, the label selector are basically the label that we have applied to any pod that will be created, which is the one that we have here. We have two labels for the pods, the app name and the version. And we will use the version later to control the traffic between the services. Then for the service, we are using load balancer, which is basically allowing us to accept traffic from outside the cluster. The service will be listening to port 8090 and will forward the traffic to port 80. 8090 is basically an arbitrary number that I picked. There is nothing stopping us from using any other number. So this is how would we deploy the first service. Similarly, we will deploy the product catalog. So we will have a deployment for the product catalog. It's pretty much similar to the one that we have seen. The only difference is going to be the container name and the image and the names of the objects. And again, we have a service sitting in front of it. And finally, for the reviews, because we have two versions of the reviews, I've created two deployments. So the first one will be deploying the version 1 of the reviews, and another deployment object to deploy reviews v2. And the reviews itself, it's logically one service with two different versions of the pods running at the same time. We will have one service sitting in front of both versions. So we have a service, and this service will be sending the traffic to the reviews. I can control which versions of the reviews if I added the version to the label selector here. But I would like to start controlling the traffic using Istio service mesh, not using Kubernetes, so I'll not add that right now. So let's go and actually deploy those three services. Can you see the font right now? Cool. So I'll use kubectl apply if, which will we can provide it with the file that we just went through. On the right-hand side here, I'm just monitoring all of the services or all of the pods in the service. All of them have been created. If I go to the Kubernetes dashboard, I can see all of the pods that have been created as well as the services. Refresh that. And if I go into any of the pods, we can see we have only one container living inside of it. So that means that the applications have been created. And if I go to the services, opening one of the services will show us the actual application. And here's the application. I can go to the product details and we'll see the product description as well as the reviews. If I keep refreshing, I'll keep getting different versions of the reviews, v1 and v2, and show you that I have created a little script that will go and will hit the reviews service and will show us which version did we get from that reviews. So as you can see, it will keep switching between v1 and v2. Obviously, on very small scale, it will not be like v1, v2 all the time. It will not be like 50-50 exactly. It will be a little bit different. All right. Now we have deployed the services. Let's start injecting the Sidecar proxies so we can start controlling the traffic. And there are two ways to inject the Sidecar proxies. The first one is to configure Kubernetes to automatically inject the Sidecar proxy to any pod that will be created inside a particular namespace, or we can do it manually using the Istio-CTL. So today I'll do it manually so you can understand what's happening behind the scene, but usually in your environment you can just configure a particular namespace to automatically inject the Sidecar proxy. So to do that, I will use the command line tool of Istio, which is Istio-CTL. We'll use a command kube inject. And the command kube inject accepts the same file that we use to deploy the services. So what will happen here is that command will accept the Kubernetes services. It will parse them, augment the file, and will create a new file. And the outcome of that new file is just another YAML file. So as we can see here, the service of the reviews, as an example, didn't change. Nothing changed in there. But what has changed is the deployment. So if we go to the reviews service, which is becoming the reviews object becoming very, very large, because right now we have mainly a bunch of annotations and we have two containers. The first one is our container, the Espresso shop reviews, and it has a bunch of arguments have been passed to it. And in addition to that, we have another container, which is the Istio proxy. And this, once we deploy those services, or update them, it will automatically start intercepting the traffic between the services. So let's go and apply this this YAML file using kubectl. Oh, sorry, kubectl. Yep. So this will go. It will terminate the existing pods and will initiate new pods. So all of them are running. My application should be working right now. And if I keep refreshing the traffic, it will keep switching between V1 and V2. So we still don't have much control over which version the traffic is going to. But we'll do that in a second. And if we open the dashboard, we can see if we opened any of the pods, that right now we're going to have two containers. The first one is the Espresso Shop Web, which is the main business application. And the second one is the Istio proxy. And this is the one that was automatically injected using the kube inject command. So what if I would like to have a more control over that traffic? How can I apply that? And to do that, I'll get back to the slides for a second. So we need to understand how the traffic routing is getting applied inside Istio service mesh. So there are two key concepts or two key objects that we need to understand, the Envoy Proxy and Pilot. Envoy Proxy is the Sidecar Proxy that gets injected to all of our pods. It's an open source service proxy, and it has been built from scratch to support cloud native applications. It's built using C++, so it has a very good performance, and it also has a low memory footprint. It also doesn't add a lot of overhead in terms of latency for the service-to-service communication. It supports a lot of protocols, HTTP 1.1, gRPC, HTTP2, TCP. It's really very powerful because it also has HTTP level 7 capabilities, so we can intercept the requests themselves and apply traffic rules based on the content or the headers as an example of a particular request. The second component is the pilot. And the pilot main responsibility, as we said, accept the rules from the users, push them to all of the sidecar proxies living in the mesh. The pilot maintains a canonical model of the services. And it also has the adapter pattern implemented, which enables the pilot to be deployed on multiple platforms. So we can deploy the pilot on Kubernetes, as we'll see today, or Mesos or Cloud Foundry, or even virtual machines if we would like to. But what if I have a cluster and I have services living on the cluster and I'd like to start controlling the traffic? So Istio itself have extended Kubernetes. So it has used custom resource definitions, which means they have introduced a bunch of new objects similar to the pod and the service and the deployments that we have seen so far. So we just create another Kubernetes object that enable us to control the traffic using them. So what are those objects? If I have a Kubernetes cluster and I would like to start controlling the traffic coming to my cluster, I need to create an object called gateway. And this enables me to start applying the traffic routing capabilities to the traffic coming to my cluster. If I would like to control the traffic going outside my cluster, then I need to have a service entry object. But what if I need to control the service-to-service communication? For the service-to-service communication, first, we need to create a destination rule object. The destination rule object enables me to partition a particular service into subsets using label selector. So as an example for the review service that we have right now, we have two versions. Those two versions could be split into, we will create one destination rule, and inside the destination rule, we split it into two subsets, V1 and V2. But so far, we didn't define the traffic routing rules, because to define the traffic routing rules, we use a destination rule to pack a virtual service object. And that virtual service object where we actually define the traffic routing rules. There is one more object, which is a very nice object, which is the sidecar, because this object enables us to tune the performance of the service-to-service communication. So if we have a database, and that database, I don't want to apply any traffic routing rules to it, I can opt out from applying any traffic routing to that database. And obviously, this will minimize the rules that needs to be applied by the sidecar, and hence gaining a bit of performance improvement. So this is an example for how would we use the destination rule and virtual services to control the traffic going between the web microservice and the reviews. So first, we create a destination rule, and that destination rule will enable us to split the review service into V1 and V2. The destination rule itself also enables us to apply a bunch of other capabilities, such as TLS settings or circuit breakers. Then, to control the traffic, as an example, to go to V1, I create a virtual service, and I say in the virtual service that any traffic going to the reviews should always go to V1. So this is how I can apply those traffic routing capabilities. So let's go and create the destination rules and the virtual services of our microservices. And then once we have that, we can, as we will see, that all of the traffic going to V1 or V2, but it's based on our decision. So here is the destination rules. The destination rules, as we said, it's just another YAML object for Kubernetes, another Kubernetes object which we define using YAML. So we have the kind of the object is destination rule. We define the name of the destination rule. And the spec section, which is the most important part, we define the host. And the host here is the service where the traffic will be received, or the destination for the traffic. Then we define the subsets. In our case, for the web, it's only one subset. It's one version. So we define the subset name and the label selector that we will use to define that subset. In this case, I'm using the version label. Similarly, for the product catalog, I have another destination rule. And finally, for the reviews, I have another destination rule that defines the V1 and V2, because this is the only service that I have two versions running at the same time. After that, we create the virtual service. I have 3 virtual services, one for each service. So the first virtual service is the one for the web. And in the spec section, we define the host that will be receiving the traffic. And here we say, for any HTTP traffic coming to the service, route that traffic to the destination rule, and the destination subset V1. And the host is the name of the service. So we have 3 virtual services, one for each microservice. And for the reviews here, we are sending all the traffic to V1. So once we deploy the destination rules and the virtual services, all the traffic going between the web, going to the reviews will always go to V1. So we'll never get those stars in the response. Let's go and deploy that. And because they are just another Kubernetes object, we will use kubectl to deploy them. So we'll deploy the destination rules first, and then we'll deploy the virtual services. They're created. Getting back to the browser. So right now, if we refresh, all the traffic will always go to V1, so we never get those stars in the reviews. But if I would like to see the reviews traffic going to V2, all what I have to do is just to change the virtual service from V1 to V2, deploy the object again, and this will immediately send the traffic to the new version, which is V2. And we can start seeing those stars. So as we can see, we started getting more control over the traffic going between the services living in the mesh. But this is really primitive. I can still apply this with the Kubernetes services. All what I have to do is just add the other label. What I can do in addition to that, which is the capabilities that doesn't exist inside Kubernetes now, which is I can split the traffic to enable canary-based deployment. So if I have a new version, canary-based deployment will enable me to send 1% of the traffic to the new version. And as I gain more confidence, I can increase the traffic going to that new version till I reach to 100% and the old version is gone. So let me show you how we have split traffic between V1 and V2. So we'll send 80% of the traffic to V1, 20% of the traffic to V2. So the way we do this is using a virtual service. And the virtual service here in the spec section, we define the host, similar to what we have done previously. And we say, for any HTTP traffic, route that traffic into 2 destinations, V1 and V2. The V1 and V2 are the subsets that we have defined in the destination rule. And the way we split the traffic is using the weight parameter, which enables us to define the percentage of the traffic that will be going to the services. So here we define 80-20. And it's pretty easy. So if I would like to incrementally roll out a specific version, all what I have to do is just keep playing around with those 2 numbers. So let's go and deploy that. we'll deploy file. Once we deploy it, and if we get back to the browser, if we refresh, a lot of the requests will go to v1, and eventually one request will go to v2. And this is how it keeps working. So I can keep playing with those numbers till I reach to 100% to v2, and then only 0% to v1. The good thing with this approach is it enables me to have more confidence as I roll new versions of the application to production. So I don't need to impact a large number of customers. I can get early feedback. And if something went wrong with the new version, I can pretty easily roll this back to the old version because I've just sent only to 1%, change the numbers, and get back to the old version of my application. In other cases where I have seen where you have microservices, I would like to sometimes test the traffic with internal users only or internal employees before I roll my application to a broader audience. So for those cases, something I can do is using the HTTP level 7 capabilities of Envoy Proxy, so I can inspect the traffic between the services. So in my application, for the service-to-service communication, I have added a header called the user role, which includes the current logged-in user, the role of the current logged-in user. So I can apply traffic rule to say, for all of the traffic coming from the administrators, send that traffic to v2, otherwise send it to v1. And it's pretty simple with Istio because it's just another rule that we can apply using the virtual service. So I've updated the virtual service to say, for the HTTP traffic that matches the following rule, it has a header with the key user role, and the value of that header contains the word administrator. If this rule has been matched, please send this traffic to v2 of the review service, otherwise send it to v1. So as you can see, with the virtual service, I can apply multiple matching rules. So if I have 3 versions and I would like to send the administrators to v2 and maybe finance to v3 and everyone else to v1, I can apply multiple rules in my virtual service. So let's go and deploy that. Use kubectl, provide it with the name of my user-based routing. And right now I have I'm not logged in user, so it's showing me v1. Once I log in as an administrator, I should be able to see v2, which is the one with the stars, and I don't want to save any of that. So this is providing us with a greater control of how would we roll my services into production and giving me early feedback as I incrementally roll out the version. So there are heaps of other features or capabilities that I can do with the traffic routing, but as you can see, it's all about playing with the traffic rules using the destination rules as well as a virtual service. Question. Istio itself doesn't do that, but there are frameworks that have been built on top of Istio that enables you to apply those rules dynamically. And you can even integrate it with like your feature flagging system. So you can play around with those values without even needing to do a deployment for a new version, but not out of the box from Istio as far as I know. Good question. So let's talk a little bit about reliability. As we have seen, all of those distributed computing fallacies is making it really hard to have a reliable connectivity between the services. And since we extracted those infrastructure concerns in the Sidecar Proxy, I kind of start getting benefits to have more confidence in terms of reliability of my overall service-to-service communication. So if one of the downstream service is too slow, and I would like to make sure that all of the requests or all of the responses doesn't take more than 1 second or half a second, I can start applying rules to do that. Because it's a network communication, I can also have rules to avoid intermittent connectivity issues. So if I have a service-to-service communication and one of the requests failed because of intermittent network issue, I can apply a retry policy. I can also have a little bit of chaos engineering in there. So if we are testing a microservices environment, it's pretty common to requests from the testing team to test the application. If one of the downstream services went down, how would the application behave? Would the whole system crash or not? This is pretty important because, as an example, if we are Amazon and the review service went down, that's not really critical for such application, because your key feature here is to show the product itself. So you might need to test how would the application behave if the review service went down. And how to test that, it's just very easy using the fault injection features coming out of Istio. And finally, the circuit breakers. Sometimes one of the downstream service couldn't accept any further connections. So how would I enable my application to keep working while this service is really slow? So I shouldn't be sending more requests to that downstream service, because if I send any further requests, most probably it will not be served. So all of those features in a microservices environment could be easily applied if we leveraged the Istio features. So I'll show you a couple of demos with one about the timeout and another one with the fault injection. So in my application, for some of the products, I have explicitly made a delay to return the reviews in 6 seconds. And 6 seconds is a very long duration. So what I have here is basically a traffic routing rule to say any traffic going to the review service shouldn't take more than 500 milliseconds, which will give me a guarantee that my system will always be behaving in or returning a response in a very short duration. So let me show you that. So here is the virtual service. I have removed all of the rules just to make it simple. And in the traffic routing section, we say for the HTTP traffic, send all the traffic to V1, but time out the traffic with half a second. So if the downstream service is too slow, I will not wait more than 500 milliseconds. Before we deploy that, I would like to show you that right now that some of the products that we have, such as this one, will take 6 seconds to return the response. So I'll just reload so we can see the response time. If I go to the network and show all, so here is my request, and this request is taking, let me put it in this side. This has taken 6 seconds to come back. And as we can see here in the reviews, it shows we don't have reviews for that particular product. So let's go and deploy our timeout rule. Once we deploy it, and if we refresh the page again, we will see that now it took only 519 milliseconds. And the good thing is the application didn't crash. It showed failed to retrieve the product reviews. It might not make sense in your case to show this error message. You might opt in for having degrade the user experience by hiding this whole section. But again, the whole application didn't crash. So the client application knows its timeout because it's basically a network error. Like right now, if you are communicating with an external service, what will happen is the Sidecar Proxy itself will not wait for more than 500 milliseconds, and once it fails, once that rule fails, it will fail or reject the request and will return the failure to the client itself. It's network error, yeah. Yep. But the Sidecar Proxy itself is the one that's controlling the timeout. So the second thing that I would like to show you is the fault injection, which is very important because, like in my last gig, what we had is a bunch of services communicating with each other, and in order to make sure that the system is always up and we have a highly available environment, we had to test all of those cases. In our case, we didn't have Istio. We used a different tool, which is called Gremlin, that enabled us to stop one of the services while it's running to make sure that the main service or the main application didn't go down. But with Istio, we can easily apply that because if I have a review service and I'd like to make sure that the review service is down, without actually bringing it down, I can easily apply that using the fault injection. So what we have here is, I have updated the virtual service to say, for the HTTP traffic, inject a fault of the type apport, and apply this fault to 100% of the traffic. I obviously shouldn't do this in production, because if you apply it, the whole thing will go down unless you know what you're doing. And the response status code with that fault injection you should return is 500, or this is what will the Sidecar Proxy return to the client. Then we have this to be applied to all of the traffic going to V1. So let's go and apply that. Once we send that, the last time this call to the review service took 500 milliseconds, but right now if we review it or send the request, it took 17 milliseconds because Sidecar Proxy immediately rejected the request because it's for 100% of the traffic. So this is really handy when it comes to service-to-service communication and making sure that the whole system is up and running, even if one of the downstream services is not really working. One of the other features, I'll not show you a demo about it, but I'll just explain how easy it is to apply a circuit breaker using Istio. So if we have the review service is pretty slow and it cannot accept any further connections, what I can do with Istio is I can define a rule to say, if I get X number of errors, 5 consecutive errors within a certain duration, please don't send the traffic to this downstream service for a certain duration, which is 3 minutes in this case. And during those 3 minutes, don't send 80% of the traffic. So I will send only 20% of the traffic to that downstream service. And this means that during those 3 minutes, I will not be sending the whole traffic. And after the 3 minutes are passed, we will start sending the whole traffic again. And if the rule applied, we will keep applying that ejection of this downstream service. So this is obviously on the network communication level. We could also have the same thing or the same circuit breaker logic in the application. But again, it's if we have both of them will be applied. All right, so enough about the reliability. Let's move on to the observability features coming out of Istio. When I think about microservices-based environment, with observability, I think about 2 key things. The first one is distributed tracing. So each microservice generates its own logs. And ideally, in a microservices-based environment, I'll be shipping all of those logs into a centralized location. And that centralized location could be Elasticsearch or any other service. But because for one particular request, I could have more than one service communicating with each other to return the response, I need to, and if something went wrong, I need to find the logs relevant to that particular request. And what we usually do is we have a correlation ID, and for all of the logs getting out of all of the services, we include this correlation ID. So this enables me to find out which service contributed to a particular error. And this is really regardless of we are using Istio or not Istio. It's just in a microservices environment, I need to have such visibility for my application. And one of the benefits of Istio, which is the mixer, as we will see, it enables us to have such capability with a very limited changes to my application, or sometimes no changes. The second thing is the matrices. What is the success rate? What is the failure rate? How many requests is coming to my request? If I have 2 versions, I need to compare the success rate and failure rate going to those new versions as long as they are running in parallel all the time. And Istio has this mixer component. And as we talked, after each service-to-service communication, the Sidecar Proxy will be sending telemetry information to the mixer. And the mixer has applied the adapter pattern, which means it can be configured to connect to multiple monitoring and observability systems, such as Elasticsearch, Prometheus, Grafana, whatever platform that you are working with. And the good thing as well is the Istio itself comes out of the box with heaps of adapters that you can immediately plug into your environment, without so much of an overhead. And the documentation is really good in terms of how would you configure those adapters to work with Istio. So what I will show you today is, I will not show you how would you do the configurations themselves because they are really well documented, but I will show you after you configure an adapter, how would you get the benefits out of those systems with a very limited change to your application. So the first demo that I will show you is about the distributed tracing. And we'll use a system called Jaeger. And Jaeger is an open source distributed tracing platform that has been provided by Uber. And it will enable us to find all of the traffic going between the services for a particular request. The second demo will be about Grafana, which is another open source that provides us with the capability to see the matrices of the services running in my platform, such as success rate or failure rate or the response duration and all those kind of matrices. Let me first remove all of the fault injection rules. And right now, if I open any of the applications, I can see that the application is running. So we'll just generate some traffic, and then we'll open Jaeger. This is the home screen of Jaeger. It enables us to see all of the services running in my cluster. And without any additional configuration after the adapter, it can immediately understand what are the services running in my mesh. And if I select one of the services, I can also see all of the requests that came to that particular service. But what if I have a particular slow service? So as we know that we have that product that usually take a lot of time to get back to us. What I have done in my application is I have included the request ID, which is the correlation ID that we usually use to generate the logs. And if I copy that correlation ID and go to Jaeger, search for that trace, I can see a holistic view of the request. And it shows me how all of the services collaborated with each other to return the response. So in this case, I can see that the request came to the web service, and then there is, from the web, I made another call to the product catalog, and the call to the product catalog took 1 millisecond. And there was another call that happened in parallel to the review service, and the review service took 4 seconds. So as you can see, with this tool, I can easily identify which service were very slow to return the response. And all of the changes that I had to do to my application was very simple. So if I go here, it's a ASP.NET Core application. Previously, I had the correlation ID anyway. So all what I had to do is just add those few headers for all of the service-to-service communication. So any request to my downstream service, I just add those headers. And this provides me with this kind of nice hierarchical view. If I didn't include the headers, I would still get the telemetry information from Jaeger, but it will be a little bit harder to understand how the services are collaborating with each other. The second thing that I would like to show you is the matrices. And actually, before we go to the matrices, one of the other nice features of Jaeger is we can see how the services are dependent on each other. So there is a dependency graph here that will show me that I have 3 services, the web, product catalog, and the reviews. And I can see that the web depends on both product catalog and reviews, and the 3 of them depends on the mixer. Obviously, the more services you deploy to the service mesh, this graph will become harder to understand, but there are different tools that will help us to visualize those services. The second thing that I would like to show you is the Grafana dashboard, which is another very handy open source tool, and it will help us with the matrices, so we can understand how the services are working in the system. Now let's just generate some traffic as well. And in a second, we can start see as well, similar to the Jaeger, I can see the services running in my mesh. So I can see the review service as an example. I can see the success rate and the server success rate. I can see the request duration and heaps of other valuable information that I didn't actually need to apply or configure my application to send anything extra. All what I had to do is just plug in the adapter of Istio, of Grafana with the Istio mixer. And the good thing that I would like to show here is with the Grafana, because if I have multiple versions running, I would like to compare the response time or the response duration for a particular version. I can see that Grafana by default grabbed the running versions, and it's showing me the response time of each version. So this is very handy because I don't have to apply any additional logic or any additional rules to my application to get benefit of all of those features. So let's summarize what we have discussed so far. So Istio is a service mesh platform that is providing us with traffic routing, observability, and security features. We didn't cover so much about the security because of time, but there are heaps of benefits of using Istio for security, such as encrypting the traffic between the services. It has rolling certificate rules and policy by server. It has a bunch of beneficial features that we can leverage in terms of security. Istio is similar to any service mesh platform, consists of a data plane and a control plane. So for the data plane, we have as the Sidecar Proxy, and the Sidecar Proxy in Istio is Envoy Proxy. And then we have the control plane components. The control plane components is the pilot, which is providing us with the traffic management as well as a service discovery. Control plane providing us with access control and telemetry. Citadel, which is providing us with traffic encryption, authentication, authorization, and generating certificates, and a bunch of security-related features. So this is pretty much what I wanted to cover. If you would like to learn more about Istio, I highly recommend reading the Istio documentation. It's really well written, and it's always up to date. If you would like to play around with Istio without having to install Minikube locally or even Kubernetes, I highly recommend Katacoda. It's a platform that enables you to spin up containers in the browser, deploy Istio, play around with it, and it's really, really handy, and it's very easy to start working with. All of the demos are available on my GitHub repo, and the slides themselves are available in this URL. So that's pretty much what I have, and I think we have time for questions. Go ahead. Istio itself has a Helm chart. So you can use the Istio Helm chart to deploy it on top of Kubernetes in any environment, regardless if it's Azure or AWS or GCP. Any other questions? Yeah. So all of those features comes with a cost. Yes, there is an additional cost in terms of overhead for the service-to-service communication, but because of the Envoy Proxy is written in C++, and they have a heaps of focus in terms of performance to not add too much overhead for the service-to-service communication, I would say that the benefits kind of cover the cost. And there is also, as far as I know, there is a plan right now to have a package that you include in your application, so there is no, to minimize the overhead, so the proxy becomes part of the code. If the performance is really, really one of the key critical things that you would like to have, and the additional overhead is kind of impacting your application, but I think it's still under development. Any other questions? So it depends on the application that you are using, but any service-to-service communication, because Istio also supports TCP, so if you have a TCP connection, you can intercept the traffic and apply it, but it depends on the application features and to what extent you would like to apply those traffic routing rules. I would expect that most of the people will be using them for like the service-to-service communication pretty much. I haven't seen it used with like Azure Service Bus or anything like that. All right, any other questions? Go ahead. Sorry, I can't hear you. Yeah, there is actually there is a standard coming out for the service mesh platforms right now, and it's just released I think a few months back. So if you are worried about vendor lock-in or something like that, then yes, there is going to be a standard that I think most of the service mesh platforms will be following. All right, I think that's pretty much it. So thanks for your time, and I hope you enjoyed the talk.